we're going to talk to not one, not two, but three rocket scientists at one time, all part of the 21st century rocket culture. They're all from Relativity Space. They're an aerospace company that relies on robotics in their manufacture of their rockets. And they're headquartered in Southern California. Again, Southern California is the hotbed of rocket design and research and headquarters. They're actually based in Long Beach, which is just a little south of us, not too far away from our last speaker, Virgin Orbit. And I would like to introduce Josh. He is a propulsion engineer from Relativity, and Josh will take it away and introduce his colleagues. All right? Thank you very much for being here today.
Thank you. It's great to be here. I think we're all pretty excited. I just want to start with sort of introducing Relativity. Like you said, we're a space startup here in Southern California. We're based in Long Beach. And I guess we're just going to tell you a little bit about how we do what we do and what we love about it. So we can go to the first slide, please. I just want to introduce what a rocket is, right? How it works. Essentially, it's a gigantic flying fuel tank. That's really what most of a rocket is. When you look at the body of a rocket, it's just fuel tank. We have fuel, which is like the fuel in an airplane or a car, and then oxidizer, which is because the rocket works in space, you need to bring your own oxygen along with you instead of using the oxygen in the air. Aside from the main fuel tanks, you have engines at the bottom to burn that fuel. You have avionics, which are the brains of the rocket. And the rocket itself has a bunch of different stages, sections that are stacked on top of each other, and they drop away one at a time. And the objective, of course, of a rocket, as I'm sure almost everyone knows, is to deliver things to space. So satellites or equipment, sometimes even crew. I'm going to talk about the engines at the bottom of the rocket, and then my colleagues who you're going to hear from in a little bit are going to talk to different parts of that design. So if we could go to the next slide, please. I want to cover sort of how an engine works. And people have often heard of Newton's laws, and there are two, but really all three are really important to how a rocket works. The third law is one that you've maybe heard of, that's every action has an equal and opposite reaction, is the fancy way of saying it. Basically, all that means is if you push on a wall, the wall pushes back on you, right? And that's the basic principle on which a rocket engine works, is you throw fuel at the back and it pushes you forward. So you can see, like, if you were sitting in an office chair on wheels and you sprayed a fire extinguisher, you would spray the extinguishing stuff out one side and it would push you in the other direction. And the other important thing to know about how this works is Newton's second law, which is written as force equals mass times acceleration. And what that really translates to for this is the faster you throw something away from you, the harder it pushes you back in the other direction. So if you were, again, sitting in a rolly chair or standing on an ice skating rink or something, and you threw a heavy ball, the harder you threw that ball, the faster and further it would push you back in the other direction. So basically all a rocket engine is trying to do is to get that to happen, to throw as much away from you as fast as possible. So if we go to the next slide, please. The basic way that you do that, like I mentioned before, you have fuel and oxidizer. Sorry, we're just waiting for the slide to come up. And you put those things into like a combustion chamber to mix it, and then you shoot it out the back with a nozzle. The rockets that we're launching today are a solid fuel, so you have your fuel and your oxidizer mixed together. But usually the way we do this on bigger rockets, although there are exceptions, is you have them as liquids and you try to mix them together. And the faster you shoot them out, as I said, the better it works. And usually the way to do that is by making them get really, really hot and burning and expanding. And the important way you get that done is if you imagine like candles on a birthday cake or something. If you blow too hard, then you blow them out. But if you blow just right, you get the flame to grow bigger and hotter and stronger. So one of the important things we try to do is inject the fuel and the oxygen to make it burn really nicely together. Like when you're starting a campfire and you're blowing on that fire, you want it just right. But if you blow too hard, then it'll be like birthday candles and they'll get blown out. The other thing is because it's so hot, it would actually melt the metal that we use to have the rocket engine. So you actually have to use the fuel to cool the engine. You have lots of tiny, tiny little channels that run through the sides of the engine that you have to build to keep it cool enough with that fuel flowing through. So if we go to the next slide, I can talk about how we actually go about building an engine to do that. And the top pictures that you'll see here are the injectors. So remember, I talked about getting a campfire to blow bigger instead of blowing out birthday candles. The way you do that is lots and lots of little holes. And the way that we used to do that, these photos are from like the Apollo missions to the moon, is lots of little tiny holes that you drill individually, and it takes a very long time. So you see off on the right, I have all the steps that you would use to make a rocket engine the old-fashioned way. The way that we're doing it as a company is we're just 3D printing the whole thing. So instead of having to machine lots of little holes and make lots of different parts to get those channels in the rocket engine so that you can flow the fuel through and cool it, all this complicated stuff, instead of having to do lots and lots of steps with lots and lots of people, basically you can just 3D print it in one piece. And that's basically the whole idea of how Relativity works. And now I'm going to give Lauren a chance to talk about how we do a similar thing for the structure of the rocket, not just the engines.
Hey everyone, I'm Lauren. I'm a structures engineer at Relativity Space. And if you don't mind going to the next slide. So Josh gave a really good introduction to how the engines work and mentioned that we have sort of the giant fuel tanks that make up the rest of the rocket. So for a quick overview of that, going from the ground up, we start with a first stage or a booster, which usually has, most times these days, about nine engines at the bottom, which are optimized for propulsion at sea level. And the booster is used to basically take everything on top of it and get it to the edge of space. And then once you get to the edge of space, you then have a second stage, which you'll separate off and sort of throw the booster away. The second stage has usually a single engine, which is optimized for vacuum. And it's designed to, instead of being like really good at picking up heavy stuff and getting it to the edge of space, it's designed to, once you're in vacuum, accelerate the payload to the right velocity so it can actually get into orbit. Sometimes you also have a kick stage or a third stage, and that's used for sort of flying control of the orbit and getting it to like a nice circular orbit. And then you have a fairing, which is like a big clamshell you'll see on top of a rocket that then separates. And that's used to protect the payload until you get outside the atmosphere so that the air resistance doesn't destroy your satellite, which usually gets you frowned upon. And then of course you have the payload itself. So everything from the engines up is essentially structures, where structural mechanics is how solid bodies react under loads and pressures, and rocket launch involves a lot of very high loads and pressures. So the challenge is to basically take this giant fuel tank and make sure it doesn't fall apart while you're sending it through this really crazy environment to get your payload into orbit. So the way that we do that is we start by designing our parts, then we analyze them, then we test them, and then we launch them. And we go through that sequence because testing your design by launching the rocket can get really expensive and really messy really fast. So it's important to analyze your parts and show that they work before you actually launch. Otherwise, it just takes a really long time. So if you'll go to the next slide, one of the ways that we do this is by, for example, this is one of our very small printed cylinders. We'll prove how capable our big printed structures are by making small scale ones and then pressurizing them and seeing what kind of pressure it takes for them to burst, and then showing that the pressure at which they burst matches what we analyze them to, and basically saying, the math that we did in advance lines up with what we did experimentally, and that convinces us that our manufacturing processes work, and we're not going to, have a rocket explode the minute we put a couple of PSI pressure into it. Then if you go to the next slide, the other thing that we do for testing, every rocket will get tested before it gets launched, and you can't really simulate the loads of flight on the ground because you have really high accelerations and really high aero loading and a bunch of stuff that's hard to get with a stationary tank on the ground. But what you can do is you take your vehicle and you put it into a big stand that has straps that go around the rocket or a big attachment at the top. And you basically use this huge test stand to apply loads and forces onto the rocket so that you can simulate the loads that you would see in flight without having to actually fly the rocket, and use that to do your final test to show, okay, the way that we've assembled this is going to live up to loads that are similar to what it's going to see in flight. And then it's safe to actually put it on the pad and launch it and expect that everything's going to go well. So the final step of this is actually making sure the rocket knows where it's going. And so Kushbu, who's an avionics engineer, is going to take that on.
Hi, everyone. My name is Kushbu Patel, and I am the avionics hardware in the loop engineer here at Relativity. Before I talk more about the role and more about avionics, I just wanted to share a quick background story. So ever since I was 5 years old, I had always wanted to be an astronaut. And being raised in Houston, Texas, I had the opportunity to visit Johnson Space Center many times and participate in STEM-related activities. And this dream of mine continuously motivated me to work hard in school, and it paved way for me to transform my goals and my passions into reality by teaching me skills needed to succeed in the outside world. I've participated in several NASA projects, and there's two that are near and dear to my heart, and one of them is the high school aerospace scholars, where I was chosen by our Texas state senator to participate in a week-long internship at JSC, Johnson Space Center, where we were able to create a mock mission to Mars. In college, I participated in NASA's Zero Gravity Project, where I had the opportunity to fly in the Vomit Comet and experience Martian gravity and lunar gravity, which was incredible. And then as far as my career, immediately after graduating from the University of Texas in Austin in 2016, where I majored in Bachelor's of Science in Aerospace Engineering, I worked at an air launch company, which you guys just listened to, which is Virgin Orbit. And I worked there for about 3 years, and now I'm at Relativity. So to give you guys a little bit about avionics. So avionics serves as a purpose of being the brain of the rocket. And the avionics, they're the electrical systems that are necessary for flight, and they're driven by software to tell them where the rocket should go. So if we go to the next slide, I can go into detail of like what systems the avionics controls. So next slide, please. Thank you. So avionics, so they tell us where the rocket should go and how it should move its engines to keep us on the correct trajectory. And to achieve this, a spacecraft actually has several brains distributed through its various components. And some of these brains include like power management system, data collection, guidance navigation systems, telemetry systems. And if you guys don't know what guidance and navigation and telemetry is, the guidance system has two main roles during the launch of a rocket, and it's to provide the stability to the rocket, as well as control the rocket during all these maneuvers that we perform. The telemetry system allows for wireless data transmissions so we can monitor where the rocket is during flight. And all these systems communicate with each other, as well as with the spacecraft avionics and command systems. But before we can put these electronics onto the rocket, before we integrate them, we have several levels of testing we have to go through to make sure that they can operate through the harsh flight conditions during launch and when we're in space with system margin. And that's where my role comes in. So I lead the design, the development, and the execution of a test system called Hardware in the Loop. HITL is the most crucial step before you fly, one of the most crucial steps before you fly. And the goal of HITL is to simulate closed loop rocket system with emulated sensors and actuators. The sensors and actuators include temperature sensors and pressure sensors, so we know how hot parts are getting, and like those are extremely crucial in also helping us like open and close different parts of the gas system. HITL testing, which is hardware in the loop, is also one of the most important tools for avionics, for software, propulsion, the guidance system to come together and really simulate what a full mission trajectory looks like. And it allows us to combine all the hardware and all the software to for a real-time, realistic feedback. And it provides all the test coverage we need to make sure that we catch all bugs and help mitigate any risks that would have occurred at the test site and launch site. So that is avionics in a nutshell. And yeah, I think Ellie is the next one to speak as well.
Hi, can you guys hear me? Yeah, so thank you so much for inviting us to speak. I have just a few wrap-up words for a little summary of Relativity Space. If you want to forward to the next slide, please. So yeah, you mentioned that we're using robotics to help to make the rockets of the future, but we're also actually using the 3D printing method or additive manufacturing, which we think will really help to accelerate the take-up of rocket launch and space exploration as we go into this new millennium. And finally, just want to leave you with a quick video. If you can go to the next slide, please. And we have a video of an example of how we actually 3D print our tank and barrels. And if you want to press the button that says play, hopefully the video will play. So yeah, that's a fuel tank that we printed in 10 days, but it looks like it was really fast. But that's the kind of thing that we're doing with what we call our massive robot, which we call Stargate. And as far as we know, that's the biggest 3D printer in the world. So keep an eye out for Relativity Space, because we're going to be launching rockets using this method very soon.
Thank you very much. That's fantastic. It's so great to see how rocketry is kind of evolving in the 21st century. This is great. And just to follow up on that, the last bit with the 3D printer, the Space Center has some 3D printers, and we've done some hands-on programming where kids are able to 3D print parts of the model rockets, like the ones we're launching today, and set them up in the space. And it's very much inspired by what we've heard you and others doing. How has this 21st century manufacturing techniques really impacted the space race, or the new space race? Is it just about making things cheaper, or has it enabled us to imagine bigger and better, or different things?
Yeah, I think Josh mentioned, the method of manufacturing for engine parts has also simplified, but yet also increased in speed. So it's literally everything you can think of: better, faster, stronger. And that sounds like a Daft Punk song, but that's the kind of thing that we're looking for. More efficiency in every process, taking the speed at which we achieve orbit or get to space and allow our customers to also get to space. Mm-hmm. The whole thing is basically a win-win situation.
I was also struck by your presentation by a couple of things. One, the historic photos, because as we've explained, the Space Center is where the Apollo spacecraft were designed and built. We've got a long legacy of aerospace here on the property we're in. But I was also struck by something that Kushbu said. She wanted to be an astronaut. So did I, and now I'm here at a space museum. How many of you guys also wanted to go into space, not just work on the vehicles that went into space? I can't see you, so I don't know if you're raising your hand. Say something.
So I wanted to be an astronaut really bad, and then I found out I was going to be too tall to fit in the space shuttle.
That's what they told me too.
That dream ended for me.
Yeah, that's what they told me too. I went to space camp and everything in Huntsville, but then I'm over 6 feet. I don't know. I'm hoping that companies like yours, you're really going to open up the opportunities for the tall people in the world. But anybody else? I know that's for a lot of the young people who are watching this. A lot of them, they think about, I want to go into space, but then not realizing that there's all of this other stuff that you can do to be a part of the space program, which is what you're all doing. Any of you anyone else wanted to be an astronaut, or have any other thoughts about how you can enter the space program?
I can speak a little bit to that. There's many ways you can be involved if you can be an astronaut, and by all means, please utilize the internet to search for science clubs at your local museums. For example, like the Columbia Space Center has a lot of organizations, like clubs and like online events like this Rocket Fever. At least when I was in Houston, Texas, I signed up for science clubs at my local school. And I also read a lot of books based on space, and I still do that a lot. Oh, nice. So I highly encourage that. I highly encourage watching films that are motivating you to also pursue this career. Apollo 13, one of my all-time favorite movies, The Martian, The Interstellar. So definitely encourage all youngsters out there, please participate in STEM activities. Reach out to your local museums, your libraries, your schools, talk to your teachers, talk to some of us engineers, and we would love to help you and guide you to that path of achieving your goals.
That's super nice. Thank you very much for opening yourself up to being able to connect more in the future with the young people out there. I want to say thank you to all 4 of you, to Relativity Space. Thanks for keeping the rocket dreams alive here in Southern California. That's super awesome. I want to thank Josh and Lauren, Kuspu, and Eliana. We're ready to keep talking to you guys more in the future. It'll be exciting to see where Relativity takes us when you guys are starting your launches and everything. So thanks a lot for being here today. Thanks for being a part of Rocket Fever 2020.